Bismillahirrahmanirrahim. In this video, we'll be discussing what is known as the driven RL circuit, or also called forced RL circuit, from Mr. Hayt's book. And we'll be discussing example 8.7 and its related practice problem, which is known as 8.9. Okay, little bit about the driven circuit or forced response is that at t is equal to 0, when the switch is closed, there is a source present. Earlier in the natural circuits or the natural RL circuit, the switch was closed and the source was removed. But in this case, now the source will remain present after t is equal to 0. That is why this is called the forced or driven RL circuit. And then if we can replace this switch and this by modifying V0 with adding ut. Now, you know the unit step function is 0 before t is equal to 0 and has a value 1 after t is equal to 0. So if we multiply V0 with ut, it is the same as if we are closing the switch at t is equal to 0. Now I have taken help of Mr. Alexander's book, since that is the book I have been following in my class. So there are two things we have to keep in mind. If you look at this diagram, this is a capacitor charging circuit actually. Now there are three portions of it. One is less than 0. When less than 0 is called the steady state condition. And then at t greater than 0, we have what we call is transient. That means the value is gradually increasing, and after some time it becomes steady state. So this is called the infinity, t infinity, or steady state. Now Alexander has taken these two portions. One is the transient portion, he's calling it IT, and the other is the steady state portion, which is called IS. And the sum of the two is the total current. I'll not go into the details. The transient is given by this equation, A e raised to the power minus t over tau, where in case of a RL circuit, tau is L over R. And the steady state condition is when the inductor becomes short circuit. So V over R is the current. So this is the steady state current, is Vs over R. And now adding the two, first of all calculating the value of A, which will be this value, and adding the two, we get this equation. And in the general form, now since this is current, infinite current, or current at infinity, this is called I infinity, this is called I0, this is again I infinity, and e raised to the power minus t over tau. Now, what Mr. Hayt has done, he has used these two formulas, and this was very, very confusing for me while I was solving the example, because the example is using this formula, but the practice problem is not using this formula. When I read it carefully, I found a very small line stating that this formula is assuming that I0 is equal to 0. So now if you compare these two and we put I0 is equal to 0, then they become the same. But in the summary, he has given this formula, which is the generalized or the complete solution, and that he is writing as F infinity, F0 plus minus F infinity e raised to the power minus t. Instead of I and V, he is using F. So F could be I. So I infinity, then I0 plus, then minus I infinity, e raised to the power minus t over. So these are the same things. So we'll be following this or using this formula actually in solving all post RL circuits. Okay, so the example 8.7, this is the circuit given. For the circuit in figure, find I for t is equal to infinity. So one is when t is infinity, you find I. Then when it is 3 minus, then 3 plus, and 100 microsecond. After the source changes the value. Now we'll explain this. What does it mean? So I can write it. This thing you have to understand. What is ut minus 3 means? The simple way to understand is that we put t minus 3 is equal to 0. Therefore, t is equal to 3. That means that is the point where the unit step function changes from 0 to 1. This point you have to understand for ut. And it is just like this, same circuit, is that we have a 12 volt and the switch is now closed at t is equal to 3. Because of this, it is closing at t is equal to 3. One more thing, as we have discussed this. Now this point was 0 earlier in the previous slide, but now this is at 3. Because of this, it will change at 3. Before t less than 3, it will be steady state. And after t greater than 0, again it will be steady state. And if we write this question in a paragraph form, then what it says that since the signal is applied as t minus 3, we need to find it for the change point at this point. That is when t minus 3 is infinity, saying t is equal to infinity. But because it is changing at 3, then actually it means or implies that at t minus 3 is equal to infinity, we have to find the value of it. Similarly, t minus 3 is equal to minus 3, t minus 3 is equal to plus, and t minus 3 is equal to 100 microseconds. So this point is important that you keep in mind. Okay, now the first part at t is equal to infinity, that means at this point, or we can write it t is equal to infinity for t greater than equal to 3. So what will happen? Our circuit is in this region. The circuit is in this region before this. That means it is in the steady state condition. And in the steady state condition, the inductor behaves like a short circuit. So we have shorted this. And we are time infinity is we are here. In this region, again, it is steady state condition. And because it is steady state condition, the inductor will be short circuited. And so this is the circuit. So I infinity will be this voltage divided by this resistance. So 12 milliampere is the answer for part 1. Now we go to part 2. Find it for t is equal to 3 minus. What is 3 minus? If you look at this circuit changing, it is just slightly before 3. That means the value is 0. And so we can say that for t less than 3, ut minus 3 is 0. And so since ut minus 3 is 0, therefore 12 ut minus 3 will also be 0. But it is in the steady state condition, therefore the inductor will be short circuited. Okay. So from here now, since the voltage is 0, therefore the current flowing in the circuit will also be 0. And therefore we can write it minus 3 is equal to 0. Okay, the next part is to find it at 3 plus. Now that means we are slightly ahead of this. Now this point we have to keep in mind that at this, within this region, that is t minus 0 or t plus 0 or t minus 3 or t plus 3, the current through the inductor does not change instantaneously. The inductor current cannot change instantaneously. However, the inductor voltage will change. Okay. So we know that I T minus was 0, we had calculated. Therefore, we can say that I3 plus is also equal to I3 minus is equal to 0. This is part 3. And then we come at part 4. We have to find IT as T is equal to 100 microsecond. Again, remember that this is after T greater than equal to 0. So somewhere here, 100 microsecond after 3. Okay, for any time T, we have to take help of the general equation. So the general equation was this, we concluded, and where tau is L over R equivalent. In case of a current, we'll just write it as current. So this is our equation. And now we can plug in the value. Now this is I0 plus, but because it is changing at 3, therefore I0 plus will be replaced by I3 plus. And so our equation will now be like this. And now we can put the values. Okay, now let's plug in the values that we have calculated. So for the shifted 3, we can write IT as IT minus 3. And the only change will be that this T will be changed to T minus 3. And tau, as we know, is L over R. So when we divide it by tau, R will go at the numerator and L will be at the denominator. So this one will be our equation. And now we'll plug in the values. These two values we have already calculated, so we'll put that. We have to calculate R over L. So this is 12, I3 is 0, 12, e raised to the power now, this is 1 kilo, that means 1000, e raised to the power minus 3 divided by L, so 5 into 10 raised to the power minus 3, and the unit will be milliampere because this current I infinity is in milliampere. Okay, and solving, we get this to be 20,000 e minus 3, and now we'll put the value of this 100 microsecond, but since it is after t greater than 3, that means it will be t is equal to 100 minus second after t greater than 3. That implies that t is 3 plus 100 microseconds. That means it is 3.0001 a second. We'll put this value here. So putting this and solving using your calculator, this is the answer. I hope you have been able to follow this. Please let me know through your comments. Thank you. I'm skipping the other part because it will become too lengthy. So we'll do in the next video the practice problem.